All right.
I lead a recorded life. It makes it easier for the world to make a bot of me.
Perfect.
Never mind. The so well, I'm happy to talk about whatever people would like to talk about. But if somebody has a question to launch with, we can start there.
Actually, I wanted to ask something if I can go first, if that's okay with everyone.
Go ahead. So go ahead. Yes, please ask.
So I wanted to ask you two things. The first thing was um if you had any recommendations for history of books on history of physics, because it you were talking so much about the history of a lot of things in your keynote speech. uh,
Uh-huh.
so if you had any recommendations for books, like how you amassed so much knowledge about history of physics,
Well,
really like
right.
that.
Yeah. So I mean, I've done a bunch of investigations of that. Like a big one I did recently was about the history of the second law of thermodynamics. And I will tell you that, given a particular question that one's interested in, like that, that particular case, there was a good series of books by a particular guy called Stephen Brush about the history of theories of heat. But he didn't really talk about the second law. He kind of avoided that. He talked about, how people realized that gases were made of molecules and so on. And, that was good for that. But then in the end, doing that, that study of history, I basically read the original documents, and that's the only way. If you really want to know what happened, that's the only hope, so to speak. And the Internet Archive, run by my friend Brewster Kale, is just a fantastic source for that, particularly for things that happened, before, for works that are out of copyright now, so things that are in the 1800s and so on. He's really scanned basically all the journals, all the books, newspapers, all those kinds of things, and you go back and you go. To me, it's really a question of can you immerse yourself in kind of what people were thinking at that time, because sometimes the way people were thinking about things is very different from the way they're thinking about them today. The issues that they thought were important are very different, and so on. So my overarching recommendation is, if there's a particular topic you're interested in, go find the original documents. And sometimes you have to go further than the published documents, and you have to go look in archives and so on. And archives, depending on, they can be better or less well organized, and you end up having and it's quite, I mean, I don't know, I find it quite interesting to go through and try and understand, there's this letter from this person to this person, and on, what the heck were they thinking when they wrote that? How did that, how did they get from what they were thinking about then to what they concluded later, et cetera, et cetera, et cetera. I mean, I think the overarching fact about history of science is that when it is written, often what people learn as the kind of simplified history of science is a story in which, people had brilliant thoughts on a particular day. And this is never how it actually happened. There's always, a decade-long build-up of people sort of understanding, getting some context for understanding something, and then finally, maybe they see that experimental result and they say, aha. But if they hadn't built up that context, they would not have said, aha. They would have just ignored it or whatever. But so I don't have I mean, my overarching comment is, if you're interested in that stuff, that, it's reading the original documents is an important thing. The other thing that's the case is that, in my experience, there are often mysteries. Like, how did somebody come to think this or that? And it turns out, in the end, there aren't any mysteries. In the end, you can unravel it. At least in my experience so far, you can always unravel, why did they think that? Like, for instance, the one I've been chasing recently, I think I mentioned this, is history of neural networks. And, a basic question there is, how did people come to think that the brain has a network of electrical connections in it? And then how did people come to sort of connect logic or something like that to the operation of neurons in the brain? And, in the case of the electrical connections in the brain, I haven't quite figured that one out. But, even from the very earliest days of studying electricity, Volta was poking at frog legs and seeing that electricity stimulated muscles. So people knew that nerves were, they had morphologically found nerves in the rest of the body at least. And so they knew nerves and electricity were connected. They didn't know, Golgi and Romani Cajal were these two neurophysiologists in the 1880s-ish time frame. And, Golgi believed that in the brain, everything was connected to everything. And Romani Cajal believed that there were synapses, separations between nerve cells. And that was a big that was the big dispute of that period of time. But nevertheless, they knew there was sort of a network of stuff in the brain. And then, for example, in the 1920s, one of the more charming ideas was that people had discovered electrons, they discovered photons, and so the idea was that there were psychons, which were units of thought in the brain. And that was which is kind of an interesting idea. And so people like this guy, Warren McCullough, thought about the idea of, there's an atomic theory of thought, and it's all about psychons. And, then, I don't know, and then the question was, are psychons related to logical propositions? Meanwhile, there'd been Whitehead and Russell with their Principia Mathematica in 1910, and they kind of, they had made this big production about how, you could think about all math as having come from logic, and so that led to et cetera, et cetera, et cetera. Anyway, these things are, it's an interesting puzzle which I haven't quite untangled about sort of how people got to this idea of neural networks and the idea of both discrete logic in neural networks and continuous weights in neural networks. So, I mean, this is just an example in the question of how one learns the general outline of history, I have to say, when I was a kid, I went to fine schools and they taught all sorts of things, and somehow, having skipped around, classes or whatever, I ended up learning the history of the 1600s in England like 3 times. And I thought, this is the most boring, unbelievably, I just don't care about the battle of whatever it was in whatever it was. And ironically, the 1600s was a period of great, subsequently, I think that my efforts to learn history then, which were pretty pathetic, it turns out later on I've kind of learnt much of the history of the 1600s because I've learnt, kind of science history, which was significant at that time. Like for example, and it's worthwhile learning a few dates, for example. Like one of the dates to know is 1642, which was the year that Galileo died and Newton was born. And that's a useful, anchor date for that period of time. But it's I don't know. I think probably in my own efforts, eventually it fills in. Like for example, I really didn't know the history of psychology at all. And I've slowly been, or of neurophysiology for that matter. And as I've been studying the stuff about the history of neural nets, I've slowly, filled in some of that. And often, one of the things that's funny, like in physiology, there are many names that I've simply never, ever heard, even though they're famous physiologists, because I've just never been involved in that field. And anyway, so I'm not sure. I mean, look, my own approach to learning things tends to be learning by doing. And so just sitting back and reading the books about history has been less my thing than digging in and deciding I'm actually interested in this very specific historical question and trying to sort of explore that particular thing. I don't know if that's, but history, I mean, it is a very interesting problem-solving thing. I mean, I find it rather satisfying when you finally figure out, oh, this is why they thought that. This is how, you know, this is how people came to that particular conclusion, because it seemed like otherwise it comes from nowhere. And then, it turns out it doesn't come from nowhere. And that to me is very useful when I think about my own efforts to figure things out. It kind of has a, knowing, getting some sense of how things were figured out before helps me to have, to understand the rhythm of what one can figure out, and also what mistakes one can make. There's a common kind of mistake is not believing the paradigm as well as one should. In other words, where you say, you figured something out, but you then kind of you sort of don't build on what you've already figured out. And you see many examples of that in history. I mean, a good example comes to mind immediately is Alan Turing. So, he figured out about Turing machines in 1936 and universal computation and so on. By 1952, he was working on biological morphogenesis. And he didn't use Turing machines or anything like that. He didn't think of cellular automata, those kinds of things, which you could easily have thought of. Instead, he kind of reverted to using partial differential equations because he thought that's how chemistry and so on works. So he didn't really, he could have built on his own paradigm in a more kind of convincing way and discovered some interesting things. I mean, I'm sort of, in a way, I'm happy he didn't, because I got to discover those things myself, and that was fun. And otherwise they would have been discovered, long before I was born. So it's kind of, why not? But I think and different people, the other thing to realize is that you learn something. Like Alan Turing was a person who would do a project and then just move on and do another project. And he didn't do this kind of grand arc of building up a huge sort of domain. Other people, sort of build these huge structures that go on for, for years, building in some direction. And it's, there are different styles of doing science. And sometimes it's more successful to do, 20 kind of point pieces of science where, where one or two of them will be big hits. And sometimes it's more successful to do kind of spend 30 years, building up some particular direction. I mean, I can give many examples of people I've known and people from history who've adopted each of those strategies. And it's really, it's more personality dependent, I think, of what one wants to do. Anyway, I think that was your first question, and now I'm finally back where I can set myself up. So I will return in just a moment here. So hold that question for just a moment. I'll be right back. Hello again. Sorry about that. Okay, we're back. Can you hear me okay?
Yeah.
Yeah, okay, good. Anyway, I was just yakking about history of science. I would say the other thing that I find interesting about history of science is, learning about the people who were behind some particular discovery or invention or whatever really helps contextualize that discovery or invention. It helps in understanding, if you try and read their stuff and so on, you know something about them, it really helps. So I'll give you an example. There's a chap I knew named David Finkelstein, who is a rather unsung hero of kind of discrete ideas about physics and so on. And but he was a person who he eventually told me, he said, because he wrote all these papers and they were hard to understand. And eventually he told me, well, the thing you have to understand is that I write these papers and sometimes I figure out that the previous paper wasn't right, but I don't say that anywhere. I just write another paper. And so it was like, there's these layers of like, what the hell is the connection between these things? And the answer is there wasn't any because he just went in a different direction. That was something that was, from the outside, it was really hard to understand that that was what was going on. There are other places where there's sort of when people claim this or that thing, if you know more about the person, you kind of know, was there something big underneath that? Or was that just some intuitive idea they had? How does it, and for example, I'll give you another example from my friend Dick Feynman. Okay, so this was a funny one. So Dick Feynman was a very good calculator of things. So he would, try and, he would work out something in quantum field theory and he would do this big long calculation and he'd get the right answer. And for me, if I was doing that calculation without a computer, I would guarantee to get the wrong answer. But for him, he found it very easy to do these calculations. So he'd then get to the end, he'd get some result. And the thing that he thought, oh, it's very unimpressive that I've managed to do this big calculation. The thing that will be impressive is to figure out some intuitive explanation for why the answer comes out that way. So he then went to a lot of effort to do that. But then he never told anybody about the calculations because he thought those were kind of trivial. And, so there were many situations in which he would come up with some intuitive argument for something. And if you say, well, why is that intuitive argument correct? You couldn't have known that without having the calculation. But he didn't tell anybody the calculation. And I didn't, after I got to know him, I realized this is what was going on. And it was very weird because, the intuition, it looks like you managed to hit exactly the right thing with the intuition, but it wasn't really the intuition, it was really the calculation, which he devalued, so to speak, which was a shame because the calculation was actually impressive to somebody like me who doesn't, do calculations, at least without a computer. So it's a funny thing. And it's also, that tends to be a thing that people, that happens with people is that the things you're pretty good at, you often think, well, everybody's good at that. That's not very notable. And the things that, you find really quite difficult are the things that you sort of emphasize the most, even though they may not be the things you're best at. I mean, I know in, I've applied this sometimes to myself. I mean, one of the things that happens when lessons of history is to apply these things to yourself and to see what you learn about what you should or shouldn't be doing. And, for myself, for example, I run companies and things like that. I have never thought that that was a thing that was at all difficult. I mean, in other words, it's always seemed to me that doing business was pure common sense and that it required much less intellectual effort than the other kinds of things I try to do. Now, people from the outside, I mean, I end up advising lots of companies and things like this, and people are sort of impressed. You're really good at this. You can figure out this and that and put this or that together. But for me, it's always seemed rather trivial compared to other things that I try to do. So I've completely devalued it and probably made mistakes as a result of that because it's kind of like, don't put emphasis on that because it's really quite easy. But so, I don't know, one of these things where people have this habit of the thing which they are actually really quite good at, they assume everybody else is good at too, and so they don't think it's very notable and they don't really emphasize it, and that can be a mistake, so to speak. Anyway, I think you said you had another question, and I've been yakking on about this one, but please go ahead.
No, like this was really, really helpful. Thank you. My second question was that how do you decide what problems you want to tackle or solve?
A good question too. I mean, okay, my approach tends to be about half the things I work on are things that opportunistically arose soon before I did them, and half of the things are things that I've been thinking about for decades. And usually what happens is, I have a general interest in something. And so I start accumulating knowledge about that thing. And I start, whenever I run into somebody who knows about that thing, I'll ask them about it and I'll remember what they say. And, I'll gradually collect papers about those things and so on. And that will happen sometimes for me for 20, 30 years, whatever. And then eventually, for one reason or another, I'll feel like, okay, I think I get it. Now it's time for me to actually do something serious in this area. I mean, this happened with, it happened with the physics project, for example. It's happened, I'll give you an example, and so sometimes those long-term things time out. So I'll give you an example. So I've long been interested in robotics, and I've kind of had ideas about how to make modular robots and things. I've done a little bit of work on that. It's pretty clear that in the next year or two, humanoid robots are going to take off in a way rather different from the way that I'd sort of imagined modular robots would work. And that project I'll never do, because that project will basically time out and the world will have solved that problem and it didn't need my approach to that problem. Whereas other things, I've long been, interested in things like nanotechnology and making things out of molecules and so on. And I've sort of accumulated knowledge about that over the course of, I don't know, 40 years or something. And that one, I don't know, that one's sort of on the edge. I think I've been thinking about this thing I'm calling subchemistry, which is kind of chemistry where you actually trace what happens to every molecule and where you're making causal graphs of what happens to molecules and so on. And so I may end up, doing that project, but I've sort of been accumulating, I'm thinking, okay, I'll give another example, which I haven't dived into yet, which is economics. I'm pretty sure that a bunch of things from the physics project and things that I've done in studying sort of computational foundations of things will have interesting things to say about economics. And I've been gradually learning over probably more than 40 years. I run into people who do economics. I talk to them. I ask them about the foundations of their field. I've been gradually building up a certain amount of knowledge, although I don't think in that case that, usually what happens when I try and learn one of these fields is there comes a point at which I feel like I can really get my arms around this field and where I really understand, where the next person I talk to, okay, so the thing that happens before that's happened is every person I talk to tells me stuff I didn't know. And where I'm like, oh, I didn't know that. I didn't know that, this thing was important and that thing was important. And it all feels like one's kind of drowning in this field. And then for me, it usually at some moment, it's kind of, you reach this percolation threshold or something where you actually understand, in broad strokes what's happening in the field. And then every single person you talk to after that, it's like, okay, yes, I get the basic point. I can see how that fits into what I already know. So, for example, for economics, I'm pretty sure I have this pretty strong intuition that a lot of the kind of, the things I've studied will allow one to say some big things about economics, but I don't quite see how. And that's one that I'll probably try and tackle sometime this year. Why? Well, let's see. What determines? I mean, usually it's a combination. Okay, so there are other things where I just have a random idea as a result of some, like for example, the stuff about Feynman diagrams and causal graphs is just a random idea that I had that came out of actually a project I didn't like very much that got done. I can tell the story. Some of the people involved in that story are right here. That caused me to think about something in a different way, and then I'm like, okay, this is interesting. I think I see what to do now, and one's off and running. I think it's one thing to say is there are very few projects that I give up on, which is sort of interesting. And every project I've given up on, almost every project I've given up on, I've regretted afterwards. And so, it's very rare. Like I found, I don't know, when I was a kid, probably 16 years old or something, I worked on neutrino background radiation. Okay, so the cosmic microwave background, there similarly is a neutrino background, and I had figured out a bunch of things about the neutrino background, and I had figured out, my favorite isotope was rhenium-187 because it's the isotope with the smallest Q value, beta emitter, the smallest Q value, which is sensitive to degenerate neutrino gas and so on in the universe. Okay, so I wrote a piece of something about this, but I never finished it, which was a mistake because it was a perfectly interesting piece of work. It didn't get quite as far as I'd hoped it would get, but it's still, I should have, eventually it's posted somewhere on the web what I wrote, but it was kind of like why didn't I finish that? It wasn't, it didn't quite get to my hopes for what it could do, but it was a mistake to just sort of abandon it. And, I can tell you, for me, somehow when we look at technology projects, for example, at the company, well, one of the things that happens, well, actually both technology and science projects, sometimes I've taken a project a certain distance and then doesn't work quite as I'd hoped, and I kind of hibernate it. And then it can come back 10 years later or something. And then, but it's very rare that I'm trying to think of other ones where I actually sort of abandoned the project. It's, I don't know what that says about anything, but it somehow, okay, so most of these projects, I feel like I have an intuition about how the project will work. And sometimes, and then I start doing it, sometimes that intuition isn't quite right. And both in technology projects and in science projects, one of the things is to not commit oneself so much to, I know how it's going to work out. And then when it doesn't actually start working out that way, you keep pushing it to work out the way that you think it should work out. And it really doesn't. And it's kind of I think it's one of the things that's sort of a non-trivial psychological issue of doing science is kind of things work out as they work out. You do some experiment, computer experiment in my case, but and it doesn't do what you expect. And it doesn't do what you hope it will do. And then what do you do under those circumstances? And I think it's super important to have the psychology that it's okay that the chips fell however they fell. I mean, that's you get yourself into terrible trouble by saying, I think it's going to work this way. I hope it's going to work this way. I'm going to move the chips so it works this way. You have to be in a situation where you're kind of, it's okay. You enjoy watching the chips, and even if they fall in a way that isn't how you hope they'll fall, you kind of follow them there. My experience has been that many of the times when that happens and they don't fall where you hope they'll fall, turns out that you just didn't think about them correctly. And actually where they fell turned out to be even more kind of as you would have liked it once you really understand it than you thought based on how you expected things would work. I mean, I think one of the, there are many examples I can think of that happened to me in that regard of kind of what, but it is an important thing. And I think it helps after you feel like, I've done some science or technology or whatever, and it's worked out okay. And this next one, to not be too uptight about whether this next one is going to work out, because it's like, if it doesn't work out, it doesn't work out. Even though you have to kind of, you do have to keep pushing or nothing will happen. I suppose another thing, another feature of this is sometimes there are many be careful what you wish for things that happen, but one of them is, one of the real traps is if you're lucky enough to do something that works out really well when you're early in your career, that is a very difficult thing to manage. And I've seen way too many people who did a cool thing, for their PhD thesis or whatever else. And then it's like, okay, what do I do for the rest of my life? And the mistake is usually always try and do something that's bigger than the thing you did before. Because what ends up happening is that just doesn't work. I mean, it doesn't, a good example, somebody who's died a few years ago, is Murray Gell-Mann, the inventor of quarks, who I knew pretty well. A difficult person in many ways, but he had been, he discovered quarks when he was a young guy. He discovered strangeness, a young guy. He was the tippy top, physicist coming into the early 70s. He was kind of the tippy top of the physicists. And the problem was that his particular approach to physics using group theory and that kind of math and so on had achieved a bunch of things, and then it kind of got stuck. It didn't manage to achieve other things. Now, whether that was because it couldn't or because he didn't look in the right directions, I'm not sure, but it didn't. And so then he was kind of like, okay, I'm going to work on other things. Like he was going to work on linguistics, he was going to work on complexity, he was going to work on other things. And every one of these things, he didn't, he wanted to do, he would only do the big thing in that area. And the problem was he couldn't, because the methods he knew didn't happen to fit. And so he got very unhappy because it was like, well, I'm trying to do this and it's not working and everybody's telling me it's not working type thing. And the thing that I think is a much better strategy is you just do what you're going to, what you want to do. I'll give a different example from the same time, actually. Dick Feynman, who, Murray Gell-Mann and Dick Feynman sort of couldn't stand each other. And they were constantly sniping at each other. And since I knew both of them, I was sometimes in the middle of this kind of bizarre sniping match between them. But, Dick Feynman was a person who just, he looked at whatever problem he thought was interesting at that moment. He wasn't really a builder of giant structures. He was much more of a solve this, solve something in liquid helium, solve something in quantum field theory, solve something in whatever, and then move on to the next thing. And at some point, he was working on QCD, and he was working on kind of pretty practical stuff about particles in QCD. And Murray was just going crazy. He's like, why are you working on this stuff? It's just, it's crummy, boring, sort of mundane kinds of things. It doesn't have any kind of, grand, it's not elegant, grand science. And, in that particular case, Dick Feynman didn't find out anything that interesting. But the point was that the rhythm of his life was such that he didn't really care that the next thing he was going to do was going to be more important than the previous things he did. And I have to say, he would, if he didn't have a project to work on, he would sometimes get into states like his longtime assistant would say to me from time to time, say, you got to go talk to him. He's working on Mayan hieroglyphs again, because that was his kind of fallback for when, when there really wasn't anything that was kind of a physics problem. But I think this thing about, I mean, for myself, I work on a lot of different things. The things that, I have no idea which thing is sort of the most important thing, so to speak. And I don't really care. And it's kind of like, there are things that I end up working on that are sort of, that I didn't think would be that important, but I did them because I thought they were interesting. And then it turns out they're really quite important. And there are other things where I think they are somewhat important, but even though I think they're important, nobody else understands them, and it doesn't, it's kind of doesn't help that much. Anyway, lots of thoughts there. Well, let's see. Any other questions, comments, disputes, whatever? And let's see. James is asking, you've got to ask these questions verbally. Is it true that Feynman would sneak into everyone's office at Los Alamos and crack each person's safe to see all the secrets? That was before I knew him. Okay, so that was, I mean, Los Alamos was before I was born, right? I mean, he told me many stories about Los Alamos. The thing with Dick Feynman and stories is that he really enjoyed telling stories, and he was really good at telling stories. But some of his stories I had heard 5 times in at least 3 different variants. So it was always a little bit unclear what, I think he enjoyed the stories more than he necessarily, was hewing to the precise, chapter and verse of the details of what happened. But I think at Los Alamos, I mean, Feynman was my impression is from what he said to me and what other people who were at Los Alamos said, he was, he had this very weird role because he was the head of the human calculators. And he was generally viewed as a very bright young chap. in this strangely sort of, in some sense, pivotal role of being, you know, okay, we want to work out the solution to this differential equation. Now this group of human calculators go start chugging your mechanical calculating machines and try and work this out. I think, you know, he sort of was a hacker of a sort. I mean, he certainly, I have no idea whether this is a publicly told story, but it was a funny one to me. You know, apparently he was at some point after, you know, he got, I think after Los Alamos, maybe, he was in a situation where he was sort of being consulted on some grand thing, and they had some whole plan of, I don't know what it was, a nuclear reactor or some such other thing, and you know, had all these plans laid out, and he really had no idea what the hell these plans were about. And, you know, they were sort of asking him for some reason of trying to kind of ask somebody to validate what they were doing or some such other thing. And he realized he didn't even know what the symbols on these plans meant. And so eventually, as he told it, you know, he sort of said, you know, he guessed that symbol might be a valve. So he simply pointed at it and says, what happens if that valve sticks? And the person he's talking to is like, oh, oh, oh. And then they start tracing it through, and it's like, oh my gosh, you know, if that valve sticks, the whole thing blows up, or whatever it was. And that sort of led to this kind of, you know, almost the mythical view of what he was doing. But the thing is, I've been in that situation many times. People are telling me there's some complicated server configuration that's doing this and that and the other, and I know some elements of it, but I don't know specifically, you know, or I'm seeing, you know, sometimes I'll get sufficiently frustrated that I'll say, show me usually there's an expletive before it, code, you know, that's underneath this. And, you know, I'll often feel like I'm in the same position. I'll be sort of pointing at some random line of code that kind of looks maybe a little bit fishy to me. And then it's like, well, and then it all unravels. So it's kind of these stories get made in complicated ways, and I don't know I think you know, you have to remember that the Manhattan Project was a very different time. It was, for example, a very patriotic time, and it was something where the view of the government was very different from the way it is today. And I think it was so, you know, and these things about, you know, meanwhile there was sort of and there were also many, I don't know, the world was different. Like, for example, one thing I learned recently, a piece of history, this guy Walter Pitts, who was one of the co-authors of the original 1943 neural network paper, he was of an age where he would have been signing up for the army in, you know, 1943, right? It's the middle of, well, it's just before the middle of World War II. How come he was writing a paper about neural nets? Well, turned out that at the time there was sort of this hack that these people who were clearly talented, you know, science people who were going to be pulled into various secret science projects, they would go and they were being sent to a particular kind of interviewer for the army or whatever, who would basically, you know, say, every one of them would say, oh, they have some psychological problem, so they can't join the army. And, you know, that was really sort of a hack so that they could go off and do these secret, you know, scientific projects for the military and so on. But, you know, it's a sort of a slightly different, I don't know, the times were different then. And so I think this notion of, I mean, I know, you know, Dick Feynman always liked kind of the hacking things of the you know, things like, you know, lockpicking. I don't think I ever, did I ever talk to him about lockpicking and things like that specifically? You know, I have such zero interest in that kind of thing myself that it would not be a topic that would have come up. I think
the story goes on to say that when everyone complained about him doing this, the solution was to say, just don't let him into your office. Instead of reprimanding him, they're like, okay, well, he's going to do that kind of stuff. So just, you know.
Well, you know, these things work. And actually, I have to tell a story about Los Alamos. There was a young chap, not so young anymore, named Tsutomu Shimomura, who was a chap I first met when he was probably 16, 17 years old. Was a student at Caltech, and he was a very early kind of computer security hacker. And he was very impressive when he was young, of being able to, this has gone wrong with this computer. Oh, it must be the blah, 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 some very detailed thing. Okay. So he drops out of Caltech. He ends up going to work at Los Alamos, and repeatedly, he didn't have a security clearance, and repeatedly, because I'd been sort of involved in getting him that role, I would get this, he broke into another one of our computers. What are we supposed to do about it? And what they realized after a while was, hey, it's much safer to have Tsutomu break into the nuclear weapons computer than to have somebody and then tell people how he did it, than to have kind of the some enemy who's not going to tell you what happened doing it. So, but it was kind of yes, the dynamics of sort of fishing him out of trouble were interesting, and I have no idea what the Los Alamos of earlier years, I'm sure, was more was probably more flexible in terms of those things than Los Alamos of the 1980s. Anyway, other questions about whatever?
I have a humble question.
Yes.
In a few days ago, in the meet and greet section, you mentioned that in terms of monads, the causal graph is kind of more primary. I would like to learn the kind of basic motivation for causal graph rather than the multi-way system.
Well, so wait a minute. There's three different things we're dealing with here. One is hypergraphs that represent the structure of space. The other was multi-way graphs that represent the different possible paths of history. And the third is the causal graph that connects the update events that are happening either in these hypergraphs or the update events that are the nodes of the multi-way graph. That are the multi-way graph has states. The states have updates. The updates are the events. And the question is, what's kind of the so those are three different kinds of graphs. They're all related. So the hypergraphs are, that's kind of where I guess I felt like I conceptually started, because that's kind of what is in the universe. Okay, it's this hypergraph. Now what happens to it? Well, it gets rewritten. And that rewrite process, you can represent that process. The causal graph is in a sense representing the process. It's kind of like the hypergraph is the data structure of what's in the universe. The causal graph is representing the process of what happens to that thing. The multi-way graph is representing the many different possible things that can happen to that hypergraph. And the multi-way causal graph is taking the events that happen and all the different branches of history and seeing what their relationships are. Now, what's more primary than what? It depends where you're starting from. I mean, you can, all three of those graphs are related. I think that from the point of view of our kind of, I kind of feel like, and I don't think I can't claim that I've fully come to equilibrium on this topic. But I feel like what matters to us about the universe is things happening in the universe. And it somehow seems more pertinent to us to know about this events and the causal relationships between events than some kind of abstract, this is the state of the universe. But I'm not sure that's, I can see it, you can look at it in different ways. And I think that's, from the causal graph, you can realize that there are many different hypergraphs that you can construct. So the different reference frames in space-time will correspond to, well, different reference frames in space-time, in the multi-way causal graph, different reference frames in branch time. These will all reconstruct different states of the universe. So a single causal graph, there are different views you can have about what the succession of instantaneous states of the universe are. And so it sort of feels a little bit like the causal graph is more primary because you can reconstruct all these different states of the universe from it. And it's kind of like one might say it this way, relativity has kind of said what matters is the relationship between events, not the absolute structure of space. Relativity says you shouldn't even think about the absolute structure of space. Now, in a typical story of the history of science, that isn't actually really quite right, because people say, well, there is no absolute notion of space. People say, the Michelson-Morley experiment demonstrated that there's no absolute notion of space. But the fact is, there is a rest frame for the universe. It's the center of mass of the universe, the rest frame of the cosmic microwave background. So one would be wrong to conclude that it's all, that there is no notion of absolute space. And that, I don't know, it's one of these things that tends to, I've observed in the history of science, that people get some, oh, we thought this, and then this was disproven, and we are sure it's that. And then they forget the previous thing, even though the previous thing is not as silly. Like another good one is the general notion of the ether. The truth is, quantum field theory has an ether, even though it doesn't want to admit it. Quantum field theory has the zero-point fluctuations of quantum fields everywhere in the universe. And in our models, that essentially is what makes the structure of space. So to say there is no ether, there is no essence of space, independent of that's just something you should banish from your theory, is actually not right. But it was something which the mathematical structure of relativity kind of led people to, oh, that can't, you shouldn't think about that, which is a mistake. And I think this probably led to led astray some kinds of thinking about the nature of space and space-time and so on. Anyway, a few thoughts. I'm not sure if that's this whole question about sort of how to think about different kinds of things and what one can learn from, for example, philosophy about that is something I'm, again, one of the things that is most tantalizing for me right now is that I'm pretty sure that there are features of the way we are as observers, which once we understand them, will tell us why we observe the universe, more features of why we observe the universe the way we observe it. And it's frustrating because I think those things will be so obvious. Like I think I mentioned, the fact that we believe we can do an arbitrary experiment is something very obvious to us. Or the fact that we believe we are persistent, we believe there are persistent objects in the world. Those things are, those are important in the way that we form a notion of, our impression of reality, so to speak. I think there are good exercises to do that try to get one out of, what would it be like if we had different sensory systems, if we were, what would it be like if we were Turing machines or something? What would we think about the universe? That's a good exercise. And it's hard to wrap one's brain around. I mean, that particular one I looked at when I was working on New Kind of Science, the idea of there's just one active place in the universe and it zips around. That's sort of an interesting view of if you believe that, if you believe there's only one thing that's ever getting updated at a time in the universe, is that a viable theory of space and time? And it isn't obvious that it's not viable, because you might say, look, it's obvious that you're getting updated at the same time that I'm getting updated. But it really isn't obvious, because if I wasn't updated, I would have no idea whether you were updated or not. And so this notion that there's, and I even worked it out in a bit more detail in NKS, that this notion that you can have this single active place that's zipping around the universe is not, it's not so totally crazy. And, in a sense, well, that's another interesting thing that comes out from our models. Actually, as I think about it, I'm not sure I could, could one think about everything in these causal graphs and multi-way graphs and so on as working that way? That is, that all you're looking at is the string of events. Every event has an ID and the events are happening in sequence. To us as observers, there would be no difference in that picture. There's nothing that says that these events in some outside the universe sense are happening at the same time. They're just, all we know is that this causal graph is getting built up. So a few thoughts. Let's see, other things. Happy to talk about science, meta-science, technology, whatever. Philosophy, maybe. History, maybe. Please.
I wanted to ask a follow-up question also. Since you were mentioning, that there are people who finish a project, then move on to another without having a big grand arc. Are there any stories where that they had this grand arc from the beginning and it turned out that it they solved that grand problem and many small problems along the way?
My own case. I mean, that's basically, look, what happened in my own case, I got interested in physics when I was a kid. I was at a time when particle physics was in really high growth phase, late 1970s. Quantum field theory was winning and particle physics was going places. And, I was lucky, was involved in a field which was in a time when there was low-hanging fruit to pick. So then it, and I suppose then the one meta idea that I had was to use tools. That is, I learned how to use computers to do algebraic computations and so on. That turned out to be really useful. That gave me sort of a superpower relative to, well, basically most other theoretical physicists, which was kind of crazy because it wasn't like it was so hard to use these things. They were okay. They were kind of experimental systems and they had quirks, and you did have to understand a certain amount about computers to not have the thing just blow up in your face. But it wasn't fundamentally hard. It was much easier conceptually, I think, than a lot of the things in physics. But for whatever reason, nobody used these things. And so that was a convenient sort of superpower. But then the real story, I suppose, I sort of maxed out the tools that people had already built in sort of doing algebraic computation. I got my PhD in November of 1979. And 1 week later, I was trying to figure out, okay, so what's my big plan, so to speak? And part of that plan was I needed to build tools that I could use to do computer kinds of things that I wanted to do. So I kind of started building this thing called SMP, Symbolic Manipulation Program, that was intended to be kind of the tool that I could use to do computations I wanted to do because the tools that had already existed weren't up to what I wanted. So I spent, a year or two building that. That was my first really big software system, and it turned into my first company. And it was, and it had many good ideas and some not so good ideas. But one of the consequences of that, which was sort of a bizarre spin-off, it's a complicated, long story, but I was at Caltech at the time, and I wound up in this bizarre kind of Twilight Zone intellectual property dispute with Caltech, which it's a long, complicated, it's quite an interesting story, and it had tentacles that went all the way back to the 1920s that sort of reared up at the time. Anyway, complicated story. But the end result of that was that I was a kind of junior faculty member person there, and I just said, okay, I quit. So, and I guess when the whole thing was sort of unwinding, I decided I'm going to work on something that is sort of just a fun thing to work on. And so I've been interested in kind of how does complexity arise in nature. I've been interested in that for ages. And I thought, I'm just going to try, seeing what I can explore with this. And that led me to think about cellular automata and start doing those kinds of things. And partly, actually, the reason I probably did that was because I was like, I'm not going to do my day job right now because I'm kind of pissed off. I'm just going to do something that I think is fun. And that turned out to be more valuable than my day job in the end. But that started me on this whole trajectory of using computation as a foundation for thinking about things. And I've been on that trajectory for 45 years now. And it wasn't obvious where it would lead. So, for example, I could tell, the physics project, I had no idea that was going to work. And I had intended to do it. I had the original ideas behind it in the early 1990s. I had intended to do it. One thing is probably a mistake, maybe not a mistake, I don't know. And the feedback from my friends, the physicists, particularly in the early 2000s, was pretty negative. It's like, we don't need another theory of physics. We have string theory. It's going to solve everything. And so I was like, whatever, I'm not going to fight the battle. I've got plenty of other things to do. I'm not going to, come up with some theory of physics and then have everybody tell me, oh, but it isn't string theory, so we don't care type thing. And so I didn't work on it at that time. And it took until 2018 before, I told the story a couple of days ago, before I, really got to jump into it. But, in the end, that whole arc of computation is an important thing for the foundations of science is a thing that, that for me is pretty much a 1979 story, so to speak. And it's been, ever since. And I keep on doing things like, for example, okay, so two things. I worked recently on these models in biology, which I started working on in 1985. But in that particular case, I didn't have the right intuition. I didn't have the intuition that I now have from machine learning, and I didn't push it hard enough, and I didn't manage to make it work. And then kind of by chance, earlier in spring of 2024, I was working on something completely different. And I thought, oh, I might as well try this example. And now that I know a bunch of stuff from machine learning, I'll push it in this way. And by golly, it worked. And so that's led to all kinds of interesting things. But, for example, my work on the second law of thermodynamics, I first got interested in the second law when I was 12 years old. So and in fact, my first serious computer program was an attempt to simulate kind of an image of a bunch of, idealized molecules bouncing around. It was on the cover of kind of my favorite physics textbook that I got when I was 12 years old. Unfortunately, many, many years later, I discovered that thing on the cover of that physics book was actually kind of a fake. But that's a different story. But anyway, my first program that I wrote probably in 1973, 1974 on a very primitive computer was to try to simulate that thing. Well, finally, I published some book about the second law 2 years ago now. So after a 50-year span, I finally managed to nail down what was happening with the second law. And, a thing that was interesting when I was first interested in that book, it was the thing that was, I realized in retrospect, I didn't realize it at the time, but the thing that was most interesting to me was that statistical mechanics is the one field of physics where you might be able to derive the laws of physics. Every other field, it looked like mechanics, electromagnetism, whatever. It just looked like the laws of physics are the way they are. We don't know why, and we'll never know why. But this is a case where statistical mechanics is a case where it looked like you could derive the second law, maybe, from the laws of mechanics. And so that was something that, in retrospect, I realized I found pretty interesting and kind of worked on for 50 years before I finally thought I figured it out. And I sort of got most of the elements of that figuring out by the mid-1980s. But the full arc of the sort of philosophical story, I think, wasn't clear until I'd worked on things about observers and physics project and so on. So it's the grand architecture of things. Who else has done grand architecture stuff? Well, I mean, this guy David Finkelstein, who had many different sort of pokings of things, was really interested in kind of how you could merge logic, physics, quantum mechanics, and so on. And I guess he was the person who actually, interestingly enough, was the person who got Roger Penrose interested in things like spin networks and so on. That was the origin story for that. I have to say, David Finkelstein was quite a character. I remember, I don't know whether I should tell the story. Yeah, it's a funny story. I'll tell the story. I was having dinner with him, and he was this guy. He had a very long white beard, and he was very, very much looked like a very sage kind of character. Okay, so we're talking about quantum mechanics, and he says to me, he says something which he says, to really understand the photon, he said, you have to be Jewish. It's like, what the hell do you mean? What are you talking about? But that was kind of in that sentence sort of encapsulated part of sort of his kind of slightly mysterious worldview, so to speak. But anyway, who else has had? I mean, in mathematics, there have been people. Bob Langland's has had this very long-running program. I mean, I'm trying to think. I mean, there are people, different fields. Like for example, here's one that hasn't worked out so well. My friend Don Knuth in computer science. His kind of big arc thing was he decided in 1966 or something that he was going to write the definitive series of books about computer science. And he got to volume 3 by sometime in the 1970s. He is now on part something of volume 4. And he had a plan for an 8-volume series of books. And he's now in his 80s. And, it started in the 1960s. And I'm afraid it's probably not going to finish. And also, he had the misfortune that computer science has not exactly been a static field over the period from the 1960s to now, which is why I think this volume 4 has had, it's like one of these things where it's receding at the speed of light, so to speak. He can't ever catch up with, finishing volume 4 because the field is expanding. But that's another example of a kind of a big arc of trying to do something. I think. Gosh, who else? There are many examples. Why am I not thinking of them? Let's see, in physics, sometimes there are weird things. Like I remember one guy I knew did early kind of quantum chaos type stuff, a chap called Martin Gutzweiler, who worked at IBM for a long time as a research scientist. And I was once having lunch with him or something, and he said to me, the real arc of my life has been about solving the problem of the moon. And I'm like, what are you talking about? And I didn't know. And it turns out the 3-body problem, the Earth, Moon, Sun 3-body problem, was the dominant problem of mathematical physics throughout the 1800s. It was the thing everybody wanted to solve. It was the thing Newton tried to solve. Didn't manage to succeed. It's another good story in the history of science that Newton, tried to compute the motion of the moon in his Principia, and he got the wrong answer. But that didn't cause him to sort of give up on the whole theory, so to speak. But anyway, so the problem of the moon was a long-running problem. Okay, so I was about a few years ago when this eclipse happened. When was that? 2018 or something. I decided to write a kind of history of eclipse prediction, partly because we'd made this website that would predict the arrival time of the eclipse to within 1 second, which was kind of interesting. It was easier for that eclipse than for the one that just happened last year because the shadow of the moon was moving slightly more quickly on the more recent one, so it was actually more difficult to get the prediction right. But anyway, But so I'm finally, many years after this comment, which I kind of remembered because it was such a weird comment, that the arc of his life had been about solving the problem of the moon, that I was studying kind of the history of predictions of the motion of the moon. It turns out he's right. This guy had spent a large part of his life. IBM had been sort of the contractor for the US government, figuring out things about lunar motion that were needed for the Apollo missions and things like this. And that was indeed the story, you know, that was the arc of what he had spent his life devoted to was that problem. And the quantum chaos stuff that he did was sort of a sideshow. So that was a funny example of that. And people, you know, sometimes it doesn't work out so well. I mean, there's a chap who was involved with our company very early on and sort of had the, I would say, misfortune of having a small amount of equity in the company, which caused him to sort of get paid a certain amount pretty much every year. And so he hasn't really had to work his whole life at this point. But he had kind of this very grand idea for sort of a way to think about computation, which I always thought was really interesting. And I was like, you should do this, you should do this. And he has procrastinated now for 35 years. And my only comment for him, he's also an enthusiast of cryonics. And so my joke comment for him is, you know, you can procrastinate even past the end of your life type thing. But you know, that's a bad example because it's kind of you know, he has this idea, it's a good idea, but somehow he has, you know, he keeps on having excuses for why he's not working on it. And that's, you know, and he will never work on it, almost certainly. I mean, it's very rare that, I mean, it reminds one of the sort of career track of people who say, I'm going to work on this thing that I really don't want to do. And then eventually I'm going to retire and I'm going to do the thing I really want to do, which is a really bad strategy because, you know, it's most of the time, even when people finally get to, oh, finally I'm able to do what I want to do. Oh, actually, I don't really want to do this. Oh, shit, I just spent 40 years, you know, working at something I really didn't want to do the thing I thought I wanted to do, but then I actually didn't want to do it in the end. Anyway, I don't, not to spread negativity, but it's not a good strategy. It's a good strategy to try and find things to do that you actually like doing on an ongoing basis, even if it's more difficult to figure out how you fit the things that you're interested in with the things that are actually available in the world, so to speak. Other questions, please. And from Shadow or anybody else. Yes, please, Pavel.
We're talking about remark. Can you hear me?
Yes, yes.
You were talking about the three-body problem. That it was a topic of the 19th century. It still is actually until now. There is very active research. You probably don't know that, but there are also advances like finding some contact geometry inside, and it's still actually for many people it's like the main research direction.
Well, look, I think with a three-body problem, the big prize with a three-body problem will be showing that it's undecidable. So, in other words, when you look at motion of three bodies, you know, sometimes they behave in very simple ways, but sometimes they tangle themselves up and it's not clear what will happen, what the outcome will be. And you could, you know, there can be an arbitrarily long period of kind of tangled stuff before the final outcome becomes clear. And I've been interested in this. I would love it. This is one of these projects which I've had stored up since about 1981 of, you know, show that the three-body problem is undecidable. The difficulty of it is that the three-body problem is, you know, fundamentally a creature of ordinary differential equations and of continuous mathematics. And the undecidability is a story of discrete mathematics. And, you know, the way you would do the proof would be something like you construct a class of initial conditions such that the three-body problem remains in a set of states that can always be decoded as discrete states, so that you can see that it follows this computationally undecidable thing. Because once you have real numbers, all bets are off. As soon as you have real numbers and you set the initial condition, like there's a configuration found by this guy called Alexeyev, there's a very simple configuration of the three-body problem. I actually had a picture of it in the NKS book, where you have two stars that are orbiting each other, and you have one zero-mass planet that's bouncing up and down, you know, out of the plane of the two stars. And it turns out that what Alexeyev showed in the 1960s or early 70s is that there exists an initial condition for that system such that any sequence of integers that will be the number of, so, you know, the planet is bouncing out in and out of the plane of the stars. The stars are going around. They have a certain period. you can have any number, you can have a sequence, 1, 13, 72, 1, 2, et cetera, et cetera, et cetera. Any sequence of integers that corresponds to the bouncing of the planet between those stars can be achieved with a certain initial condition. And that initial condition is, it maps onto the shift map. You are basically excavating the digits of the initial condition. And we can't hear you, sorry.
I'm just thinking here that I actually implemented something similar in Mathematica. That basically, if you have two bodies, then you can basically near the Lagrange point, you can start searching for initial conditions such that given any infinite sequence of numbers, you can make it so that it goes 3 times around Moon, then 4 times around Sun, and so on. And this is a very peculiar property of the 3-body problem. This would not exist in a combination of two-body problems. This is something what first one considers more, but it was just a remark. And these are really it's still very active area of research. But it was just a remark.
Actually, I don't know how. I think it's in small pockets. I mean, I know there's been this idea of linking computation theory to the 3-body problem is something that has not. There are a few people know about this issue. But that's going to be the real thing. What was shown in the late 1800s, right, and what Poincaré worked on and things like this, was that there are no algebraic invariants of the motion. That there are no, just like in the 2-body problem, you have, energy conservation, you have the conservation of the Runge lens vector, you have the elliptical orbit, it doesn't precess, and so on, and at least in a inverse square potential. It was proved that there are no algebraic invariants of the motion, but then this guy Sundman found the solution, although it's a big messy thing. And I think this idea, and then it sort of got wound up with dynamical systems theory, which is very much a creature of real number, excavating digit type thing. Anyway, if you're interested in the 3-body problem, go solve it. Go figure out that it's unsolvable. I think it's really it will be a dramatic. I'm sure that the result is correct. It will be a dramatic moment for the realization that sort of computational ideas are important in mathematical physics, so to speak. I think that's one. The other one is the 3D Ising model, proving that something like that the phase transition temperature of the 3D Ising model is non-computable, would be another example. Now, I have to say I was saying earlier, the trick is to not have one's hopes up about where the chips will fall, so to speak, when you do any of these investigations. And I have no doubt that if one really digs into solving, proving the undecidability of the 3-body problem, or the, non-computability of the Ising model critical temperature or whatever, that what will actually happen will be more complicated, more bizarre, and more unexpected than one imagines, so to speak. In other words, that's a good initial guiding principle, but one shouldn't, in the case of the 3-body problem, my guess is that to solve that problem will require a different way of thinking about matching up real numbers with computation. In other words, that's been a thing. The matching of real numbers with computation has been a challenging kind of, it's not been clear how that works. In the case of integer computation, there's a very robust model of computation. Turing machines, combinators, lambda calculus, they all correspond to the same class of computations. In the case of real numbers, there is no similarly robust definition of computation. So that's one of the sort of challenges which might get addressed there. Anyway, but no, I'm glad to hear. I'm a big enthusiast of the 3-body problem. James is asking, is it related to the 3D random walks? No, it's not. One of the features of these types of problems is their details matter. Sometimes there's some areas of science where there's sort of enough universality in what's going on that it's kind of like something that's vaguely similar to something will actually be connected. There are other cases where it's not. And I think the three-body problem has a very definite mathematical structure that is complicated. Even you've got the three bodies and they're all, rotating around each other. What coordinate system do you pick to understand what's going on? Even that is a big, complicated mess. Anyway, but I'm glad you're interested in the three-body problem. Yeah.
It was just during my university once organized some seminar, and actually it was some Mathematica thing that I wanted to implement. But I wanted to ask you about these hypergraphs. So if you talk about hypergraphs and physics, what do you imagine under the dots and under the edges and so on? And also another thing, so what would you imagine? I mean, I can imagine if you talk about applications to computers, you imagine some data structures and they're writing rules or some programs which transform one data structure and another or whatever, and you have some hypergraphs representing it. In economy, I could probably also imagine that it's some contracts between people or whatever, or flow of money. But what do you imagine in physics? How actually should the mapping to the real world look like? And another.
Okay.
Yeah.
Go ahead. I mean, we have some philosophers here who will probably find that question, I don't know what to say, but it's okay. So the issue is, what is a model? The fact is, this is when you say that, for example, let's take the three-body problem. The three-body problem, the bodies move according to differential equations. But there's nothing that implements the differential equation. There's no Mathematica running inside the moon telling it what to do. It's just that the differential equation represents what the moon does, so to speak. And so it is with these hypergraphs and so on. They're a representation of what the universe does. They're an attempt to make a bridge between what the universe does and what we can think about with our minds. There's no sense. I mean, the fact that computational things can be implemented with semiconductors and electronics and all this kind of thing is just as any theory we have can be implemented by us thinking about it in our minds. But the fact is that there is no, the substrate is the universe. It is merely a representation of what the universe is doing. So it's not that the hypergraph is running on a computer. The hypergraph is representing what the universe actually does. Just as the differential equations of the three-body problem are representing what three bodies do, they're not what is mechanically running in the moon, so to speak, to get it to do what it does. So there is no substrate. Now, the interesting question is, perhaps a more philosophical question, is why we have an abstract description of the world. Why is there any reality in the world? One way that people sometimes describe that is what puts the fire into the equations. We have an equation which is abstractly describing the world, but why is there any actual reality to what's going on? And I think I have a little bit of an understanding of that now. And it has to do with the fact that the Rulliad is this necessary object that has to be the way it is. But the sort of within that, there's us as an element of that are observing it. And the question of whether, let's see if I can do this in real time. This is always, doing philosophy in real time is really hard. The way to think about, so I mean, let's see. The existence of the Rulliad is not a matter of debate. It is a necessary object in the same way that if you've defined plus and equals and so on and defined numbers, 2 plus 2 necessarily equals 4. There's no debate or discussion or whatever about why it is that way. It is given the definition of the terms, it must be that way. And so similarly, the Rulliad is of the same character. Once you have defined the notion of computation, the Rulliad is an inevitable object. So now the question is, so it abstractly exists. It is an abstract thing so now the question is, well, why, then we have to explain, why do we exist? What is, if we are part of this Rulliad, but why is a thing that can observe the Rulliad in the way that we do it? Why do we exist? And that's a science question, which one could try and address. And I don't think we're all the way there of understanding why it is it is perhaps inevitable, perhaps not. Why? Well, in the end, it must be inevitable because there's only one Ruliad and we exist in it. And so the question is, why are there observers like us within the Ruliad? And why are there observers who have finite minds, believe they're persistent in time? I realized recently that an important part of this whole story is that there are many of us. If there was just a single mind in the universe, it would be it's not clear. Our experience of there being an objective reality, I think, is not unrelated to the fact that there are many of us who kind of more or less agree on the objective reality. If there was just one of us, it would be much harder to, at least we have the impression there are many of us, and that gives us also the impression that there's an objective reality about which we all agree. But if there was just one of us, it would be much harder there would be nothing to bounce that objective reality off. And so one of the questions is, well, it sort of ends up being a question that ties into foundations of biology, actually, which is sort of the fact that there are many of us that are all quite similar enough that we can sort of appreciate the same concepts. There's a question of how does that work? How does one get, self-reproduction, things like this in the system? And I don't know the answer to that yet, but it's something I've been interested in recently. And I hadn't really realized the connection between what seemed like sort of a detail of biology and something that seems like it's more globally, philosophically important in our way of understanding the world. So a few thoughts. So the answer is there is no, the question of how, by the way, the question of how best to represent the hypergraphs and the multi-way graphs and the causal graphs and so on in a computer, that's a non-trivial question because much of the detail of those graphs doesn't matter to us. In other words, we can draw out this hypergraph. We can say we're going to lay it out in this particular way. We can, et cetera, et cetera, et cetera. It's very arbitrary. It's the same thing that happens in traditional general relativity, for example. If you're trying to lay out a space-time, there is total arbitrariness in the way you set up the space-time, and all that matters, and those gauge degrees of freedom cause endless trouble in actually, computing things because they're just sort of flopping around. They don't matter. And the three-body problem is another good example, actually. Imagine if you're doing the three-body problem and you know the actual coordinates in some XYZ coordinate system of the three bodies. That's one thing, but it doesn't matter. We know perfectly well that you can translate the three bodies to a different position. You can rotate them around, all those kinds of things. Those don't matter. So really, you should be modding out by those characteristics. But when you do that, the sort of XYZ coordinates are very easy to understand. By the time you've reduced it to some other coordinate system, you end up with this very complicated coordinate system with lots of weird constraints. And so that's a very common kind of trade-off, which we have not fully figured out in the case of the physics project. What is the minimal, we know that, for example, global multi-way graphs are deeply inefficient. In a global multi-way graph, you're making a copy of the whole universe at every point in the multi-way graph, which is completely crazy because two nearby nodes in the multi-way graph differ only by a single event in what happened in the universe. So most of the universe is completely identically copied between those two states, between those two different states. So, local multi-way graphs are one kind of approach. I had this approach I was calling multi-space, which is a way of trying to reduce the number of degrees of freedom to the actual degrees of freedom that matter. But as you do that, it becomes more and more difficult to sort of manipulate those degrees of freedom. So anyway, just a few thoughts about that. Let's see. Whoops. What else would people like to chat about? I'm trying to resize my thing on my screen. Why doesn't this work? I can't see you all because I'm not, there we go. There we go. Okay. Well, if anybody else has other things to ask about, I'm happy to chat. Otherwise, I'll start asking you guys questions. That's the other.
Then I could still ask on the same line as I was asking,
Please.
maybe. So you are always talking about modeling the whole universe. So you are not thinking about modeling like some atom or whatever like that. So I mean, if when you are talking about the graphs, so you are not thinking how I would imagine that you would make some connections to physical models, that you might come to some point that the graphs are sufficiently complicated, that you have sufficiently good rewriting rules or whatever, and they form some algebra, let's say, on the space of linear combinations of the graphs or whatever, and then you obtain some representations of algebras which you know from physics or something like that, and it would be correspond to some particle, to like canonical momenta and canonical positions or something like this. Is this the way how it is envisaged, that there, in principle, if we really try to connect it to what we know,
yeah.
and to okay.
Yeah, I mean, probably not that particular path. I mean, the things we know are things like limits of hypergraphs behave, follow the Einstein equations in the same kind of way that we can show that limits of molecular dynamics follow the fluid equations. It seems that we can show that limits of these hypergraph rewritings follow the Einstein equations. But now what you're asking for in terms of particles and canonical coordinates, things like this, my guess is that's the wrong approach. I mean, it's similarly, if you think about molecular dynamics, you can get from molecular dynamics to fluid dynamics. Let's say you're given molecular dynamics and you're asked to derive rigid body mechanics. That's very hard because rigid body mechanics is a weird limit of molecular dynamics, and in which the number of degrees of freedom has been sort of artificially reduced. Things like conical coordinates, I think, are the same type of thing. I think they're some of the later stage things, I think, to get out of these kinds of models. But I think this question of, are you modeling, okay, so for example, with cellular automata, I never thought of cellular automata as models of the whole universe. I didn't think they would work for that. So cellular automata have been used as models of a zillion different things, from social science to biology to physics to astronomy, et cetera, et cetera, et cetera. They're used all over the place. They're kind of minimal models that are useful models of things. Hypergraph rewriting is another type of minimal model. So a cellular automaton is a good minimal model of something where there is a rigid structure in space and time, and you have discrete states, and that is sort of the general case of models of that kind of structure: locality, discrete states, rigid layout in space and time. Hypergraphs are, again, very interestingly, a sort of fixed point of studying many kinds of things because they have no structure of space. They have arbitrary relations between things. And so hypergraphs, it's been interesting because a bunch of things we've looked at, whether it's in machine learning, for example, it's like, well, actually, we might as well look at that in terms of hypergraphs. It's not, I think it's one of the sort of few fixed points of a typical model that you might want to study. I mean, in statistical physics, things like the Ising model have been sort of things which keep on coming back as things that are useful things to use to study things. So I think there's a different direction, which is to use hypergraphs as models of specific systems in, economics, even physics. Don't know of that case so much. Am I thinking right? Well, multi-way graphs end up being useful for a bunch of things in statistical physics. I don't think that's been as well worked out. I worked out some things to do with aggregation systems, but I think the whole idea of partition functions is something very closely related to multi-way graphs, and there's probably a bunch of things that can be figured out there, but I haven't figured them out. So it's, but yes, the whole story of one is starting from a very low-level machine code, and one is getting to the things that are known in physics. Some of them are easier to get to than others. It's just like if you say, I've got my computer and it's running this operating system, and all I know about my computer is the underlying opcodes that run in machine code. It's, some things are obvious about what the computer does from the nature of its machine code. Other things are really not obvious at all and take a significant effort to kind of go from that level to the level that you're observing things. Right, let's see. Anybody who hasn't said anything is welcome to, or people have said things as well, but otherwise I should disappear fairly soon, but I'm happy to chat a bit more. James or Dugan or Xerxes, do you have things that you think I should make sure to try and address or talk about?
You know, why is space three-dimensional?
I don't know.
Are you glad that it is?
What would it be like to live? That's a good question. What would it be like to live in flat land or in four-dimensional space? Look at that. Dugan is walking away, and that might be a sign of something of
Just
demonstrating three-dimensionality.
well, in 2 dimensions, we wouldn't be able to have a digestive tract. That would split the organism in half, right?
So what? I mean, I think that's
so you would have to be amoebas that sort of osmose your material.
Yeah. Well, what would happen in 4 dimensions?
You wouldn't be able to tie your shoes with strings. Knots would unknot themselves because there's too much room for them to sort of unwind themselves.
So you mean wait a minute. Okay, that's an interesting claim that a shoelace wouldn't work in 4 dimensions.
It's from dimension 4 higher, all the knots are basically unknot, are trivial, can be homotopy to each other. There is no Borman rings or any phenomenon.
Yeah,
like
yeah, right. I mean, but shoelaces don't work the same way because shoelaces are not closed knots. So it's completely obvious to me. I understand that a closed knot is always the unknot. Is it obvious for shoelaces as well? Why would they be? That's not totally obvious to me. It would be a fun thing to actually simulate to see why to just make a 4D, what happens when you pull on the ends of a 4D shoelace or 4D knot, 4D knot, a knot of the practical knot where there's pieces of strings at the end.
I guess the shoe is
the intuition is like, oh, I'm sorry, go ahead.
You could probably imagine it like with color, right? The 4 dimension, that when it gets kind of to the moment that you are unknotting it, then one becomes red and one becomes blue, and they unknot in this color space, and then they again go to the same color again.
Probably so. It would actually be a fun simulation to see. I mean, it's but look, the fact is that the question is not, I think, why we quotes are 3-dimensional, but why we parse the world as being 3-dimensional, because we don't have to. We could parse the world by just being 1-dimensional and just zipping around, and just seeing this 1-dimensional thread. I mean, like for example, in like the image that I'm seeing of you, okay, is actually not 2-dimensional. It's actually a bunch of scan lines. Well, actually, I don't know whether that's the case in modern times.
Not anymore. That's the case for CRTs.
Right, but when does the update happen? I see. It's a direct memory transfer, so all the pixels get updated at the same time. Mm-hmm. Yes. Okay. So we went from 1-dimensional. So in the time of CRTs, we were fundamentally 1-dimensional in our image acquisition, and now we're 2-dimensional, which is also not 3-dimensional. And if I don't know whether you've used the Vision Pro, whether you've done a video conference with somebody with a Vision Pro, but that's 3-dimensional. It's also pretty weird.
Well, that's two-dimensional. I mean, we still have 2-dimensional retinas.
Indeed.
At the end of the day.
Indeed. But nevertheless, we have, I mean, I think the question is, why is our way of parsing the world is 3-dimensional? And for example, as I've mentioned a few times, I mean, the fact that we believe in space is a feature of the different scales. I mean, the fact that we believe that it is worthwhile to think of an instantaneous state of space that changes to another one at a different time is a consequence of the fact that when we look around us, light comes to us from where we're looking around in a time very short compared to our thinking time. If our thinking time was much faster, we wouldn't believe in space. So the fact that we believe in space at all is a consequence of that feature of us. So now the question is, why do we believe in three-dimensional space? And it's going to be something as obvious as that. I have to say, because the fact that we believe in space is as you start thinking about it, you realize that it relies on these scales. And so, go ahead.
There's a psychological/biological reasoning I heard once, which was, when we're floating around the primordial soup, the only things that we could think about were moving left and right, forwards and backwards, up and down. And then for more advanced creatures, it was detecting heat as well. So maybe it's something psychological that just like exposes us to 3 dimensions of space.
I don't know. I mean, it feels very real, right? But the fact is that the fact that things feel, one of the things one learns from dealing with computers a lot is that things can feel really very real without being that way. Like, for example, the pixels on a screen are not terribly real, even though we certainly have the impression that we are having, it's a real image of a real person, et cetera, et cetera, et cetera, even though deconstructed, it's just a bunch of pixels on the screen. And so, this idea that, there is three-dimensionality and we can pick up objects and they have, some reality to them, it's very deceptive. And I agree that it's kind of, the inner impression of what the world is like is, I mean, it feels very real. It is sort of our nature, I think, to I mean, when you start doing thought experiments about what would it be like if we replaced our brain with a computer and things like this, and would it still feel real to us? It's pretty obvious the answer is yes, it would still feel real.
Because we can recreate what our senses are doing.
Well, what is our inner feeling? I mean, it's kind of like, we could be, a computer has inner feelings as well. They're a bit different from ours. But I don't have any reason to think that the inner feelings of a computer any less relate to the reality of the world than our inner feelings do. But the question of whether...
So like our feelings are based upon our sensory impressions.
That's how we
I mean, that is our like input. That's our bandwidth.
Yeah, but that's how we express them. I mean, the fact is that we could have, the fact that we use words, we communicate things. I mean, for a computer, for example, how many dimensions of space do you think a computer thinks there are?
It has no frame of reference. It's not really embodied. It's not trying to scoot around the environment.
Well, but it's on the internet. And so, for example, it knows ping times of computers, of other computers. What's that?
That's a type of embodiment. There's a cybernetic embodiment.
Yes, right. But I mean, what dimension of space does the computer think there is out there? If it thinks from ping times, I don't know. Actually, I need to do that calculation again. If somebody feels like doing it, it'd be a fun thing to know. What is the reconstructed shape of space based on ping times? So, for example, you might think that the ping times would tell you that that it's two-dimensional, that space is two-dimensional because it's on the surface of the Earth. But I don't think that's true anymore. I think that was true, but I think now well, it depends. When you get down to speed of light restrictions, that's one thing. But I think the way the trunking has worked for fiber optic connections around the world, it's a much more bizarre topology than that.
Yeah, the network topology, that's what you would be feeling your way around in.
What, in the network topology?
Whatever, yeah, you have, servers, and then those are connected by larger cables. And
right, but that's probably how that's arguably how space works too. I mean, it's just that the cables, notwithstanding Pavel's comment, I mean, the cables are merely a representation down at the level of the microscopic, atoms of space. But the question of what, these cables for computers happen to be, we can see that they are embodied in pieces of fiber optics and so on. But the question is, I mean, of the billion computers that are probably, I don't know how many it is these days, few billion computers that are on the internet. I mean, we blew out of IPv6, so that means it's let's see, how many? Let's see, 140.177.200. That's nine decimal digits, so that's a billion, right? So that's the number of computers on IPv6. So we know it's more than that. So it's probably 10, I don't know how many, 5 billion computers or something. That's enough that you should be able to form a pretty good picture of what space is like. If you knew the ping time to every one of those computers, what is the shape of space? And
it's like a spider web in that context.
At 5 billion, it isn't a spider web. It's something more continuous.
Okay.
I'm sure. I mean, I'm sure it's we could probably apply inverse geometry ideas to the structure of the web or the structure of the internet. And actually, this is a calculation. We should do this. We should figure out what the effective shape of space is. Because I know back ages ago, I looked at this, and you could definitely detect the two-dimensionality of the world based on the connections between computers. But I
Right,
don't.
it's all on the surface then, yeah.
What's that?
It's all on the surface of the Earth, right?
Yeah, right. But the problem is that as I say, if you optimized things and there was no latency in switching and things like this, then it would be all speed of light connections, and it would again map onto the surface of the Earth for now, at least. But I'm pretty sure that that's not how it works, because the actual, the ping time from, like I was just looking at a ping time, it's 126 millisecond ping time, which is to 2,000 miles, and that's way bigger than the speed of light time for that same distance. So it's just like, if you look at in humans, our human reaction times are a third of a second or something, yet the neural transmission times are, that corresponds to the signal from the eye to the finger going about 100 meters at the speed of neural transmission. So it's kind of all, curling around in one's brain type thing before it gets out to the afferent nerves to go and to go and push the button type thing.
I had one more question, but I don't want to ask a bombshell question too close towards the end of your time. But I'll ask it anyway for reference. Would you be able to summarize what would be like the crux of the difficulty in getting quantum mechanics and general relativity to be unified? Like, what does it kind of boil down to for us non-physicists out there?
I mean, they're theories that came from very different places. In our models, they're theories that are deeply connected. I mean, the multi-way causal graph, one slice of it is quantum mechanics, one slice of it is general relativity. And we don't know all the details of that, but that's the qualitative picture, and it probably is similar to the ADS-CFT correspondence that people have found or think, have kind of imagined in traditional quantum field theory and so on. But I mean, the problem is, the traditional problem has been quantum field theory tries to be underneath things, and quantum field theory has, if you try and do quantum field theory for gravitons, it doesn't work in the usual way that you set up quantum field theory. But the fact is that's, the idea that there are particles of gravity is, and that you can sort of account for them using the same kind of formalism of quantum field theory just doesn't happen to work. But that is, I think, I can explain the technical reasons it doesn't work. I mean, we're going to see how this works pretty soon, I think. I think the stuff on Feynman diagrams is going to, because the thing that goes wrong in traditional quantum field theory applied to gravity is, okay, in quantum electrodynamics, theory of electrons and photons, there are Feynman diagrams that represent the space-time sort of causality of interactions. And there are loops in those diagrams that are things associated with, for example, the self-energy of the electron. The electron is an electrically charged thing, and it has, the electron repels itself. And that's represented in a Feynman diagram that has a loop, and the electron is infinitely small according to the standard theory, and so it infinitely repels itself. And that shows up in Feynman diagrams as these integrals which diverge. Okay, so you've got all these divergent integrals, and so everything's infinite, and how can you conclude anything? Well, it turns out there's this trick that Dick Feynman figured out in the 1940s called renormalization, and the main trick is there are only 3 independent infinities in quantum electrodynamics. And so, for example, the electron self-energy is, you could say, well, what would the mass of the electron be if it didn't have all these photons around it? Well, maybe it will be minus infinity. Okay, so then it has all these photons and they add plus infinity. And the result is we just observe the mass that we observe. And you only have to do that hack 3 times in quantum electrodynamics. And that is why it's called a renormalizable theory. In the standard way that you would do that for gravity, with gravitons, there are an infinite number of infinities. Every different loop gives a different infinity. And so you can't do that trick. So you can't say anything from the quantum theory of gravity made up that way. Now, I think that the stuff we're doing with Feynman diagrams now, which hopefully we will understand how renormalization works at a very base level there. And then I think the relation of that to our causal graphs and the multi-way causal graph, I'm sort of hopeful that we'll end up really being able to see why it is that renormalization can still work in the case of something which would sort of mix together space-time degrees of freedom and particle degrees of freedom. But that's
kind of renormalization is kind of the thing to tackle, to merge the historic theories.
Maybe. I mean, I think it's much more, that's a symptom, not a cause. That's a symptom of something going wrong. And, you know, it will be cool to see how that unravels, but I'm not sure that's the key point, so to speak. Anyway, I saw Sandra coming on camera just for a moment, which might have suggested a question in the making, but perhaps not. Now you're brighter lit than you were earlier.
Just enjoying listening. So it's very interesting.
Good. Well, let's see. Reza also. I unfortunately do have to go in a few minutes, but I probably have, if you want to raise something, please.
Yeah, actually, I wanted to ask a question from the beginning, but because it's irrelevant to the current discussion. I've just waited to finish. You know, you told us that you spent some time to accumulate some knowledge about something that you didn't know, and starting learning it to the level that you can do research. I wonder how you do that, by reading books or papers. What's your starting point? Because I prefer to just start from a book to understand everything from scratch. But sometimes it's really time consuming, and in the end, maybe you don't end up doing something in the research. You learn stuff, but you can't do research because you just read books, not papers, and maybe you just lose the motivation when it's time to just go to the papers and find out that, okay, I don't still understand fully what's happening in the research papers. What should I do? And just that's one of my questions, because it's really recently I got interested to quantum chaos, and I started reading a book. I don't know if it's a good strategy. I should go straight to the papers or books. That was my question.
First point is that I find it really hard to study things when I don't have a question that I'm trying to answer. So, you know, given and in any field, it's usually the case that one of the strange things is the foundational questions have often not been addressed as much as they could have been. And so my strategy tends to be, you know, what is the foundational question in the field? So in quantum chaos, you know, we can talk about, things about, you know, what does it even mean to have a positive Lyapunov exponent in a world where there's a Hilbert space of blah, 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 but forget the technical details of that. But you know, for me, it's always, I ask, you know, there's a question I want to answer. And then what I learn outward from that question rather than learning. I mean, as I mentioned before, one of the things is that often there are questions which I've wondered about for years and years and years. And so I'll run into people from time to time who know about those things, and then I'll ask them things and I'll gradually accumulate knowledge. But it is rarely the case that I just sort of hit the textbooks to try and learn the field. I will say there's one trick with learning fields, which is if there are textbooks written by kind of founding people in the field, I have found that the introductions to those books are usually quite useful. In other words, the technical detail you drown potentially, but the introduction, the people say what the main point is often. The people who are not the real founders of fields, they may not even know what the main point is. They may only be talking about the technicalities. But when you get, these kind of the somewhat less guarded, I'm just going to tell you what the main point is things from the people who started a field, that's often a useful place to start. And sometimes you have to kind of entwine a bit with the history of the field to know, like with quantum chaos, I would strongly suspect that if you want to understand what's happened there, you have to know something about the history, because the history will be, I think it has some twists and turns, and where it's like, well, why did people study that? Why is that important? Well, maybe it's because historically something else was believed, and so people went down that path. And maybe it isn't, in fact, that important. But I found that, for me, I am very much of a build it for myself type person. And I'll get to specific questions where I will have some sense, will people have answered this question or not? And then I go find out. And that requires drilling into the latest research papers, maybe asking people and so on. But it doesn't work until I have enough sort of definiteness that I can ask a specific question. Like I was asking, I don't know, like I've recently been studying the foundations of medicine, attempting to formalize the foundations of medicine, which is a spin-off from this biology project of mine. And so I got to a certain point thinking about that, and I thought I better find out what anybody else has said about this. My guess is nobody's said much about it at all, okay? And so I found this interesting article about the philosophy of medicine, that when I first looked at it, when I was first thinking about this project a couple of months ago, I kind of like, I don't get it. There doesn't seem anything interesting here. Now that I understand more about this project, that article is actually quite good. And it's quite a good checklist of kind of things that people have wondered about the foundations of medicine, so to speak. And it was kind of, if I looked at it too soon, it was just gonna, I was just drowning. I couldn't tell what the hell was going on. I think, but again, my own strategy tends to be find a problem. I'm driven by, can I solve this problem? And in the case of, in the case of economics, for example, a field that I'm trying to look at, sometimes in these fields, the question is, what's the question? Like, it's not obvious what, economics, all we know is people make all these pronouncements about economics, and they often don't seem to know what they're talking about. And there feels like there are scientific things you can say, but it's not clear what those are. And that's a case where I don't know. There may be a theory of economics which has a theory of some quantity that is irrelevant to practical economics, which is like, well, this is an interesting theory, but which could be perhaps validated, but it doesn't happen to tell you how to invest in the stock market or whatever. I mean, there are other fields like neuroscience is another field where it's like, the question is, what's the question? To me, the obvious question there is there an intermediate level of description of how brains work between pure neurons and psychology? And we don't really know that yet. And that, which is the same question as comes up for LLMs, whether there's a level of description of LLMs that is below just, well, it produces this sequence of words, and above, it's got these weight matrices and so on. So But, you know, I think, I mean, understanding for these fields sort of what the question is, yeah, I mean, it tends to, you have to kind of gradually absorb the kind of the feeling of the field, so to speak, to get to that. And sometimes, you know, you might ask, why would I work on a field where I don't even know what the question is? And that's a reasonable question to ask. And you know, economics, I suppose I'm interested in that just because it has all these actual tentacles in the real world. And, you know, and questions like, well, for example, actually one question that got me into this a bit was, is cryptocurrency fundamentally worthless? Okay. To which the answer, I am sure, is no. It's not fundamentally
It depends on the utility.
That's what economists say.
Okay.
I mean, you can't buy a cup of coffee necessarily with it, but it could be the case that as a store of value, it's a fine store of value because everybody believes it has value. And so you've built up this complicated network in the world where the world would fall apart if it didn't have value. And, you know, and so that means it actually has value, whatever that, you know. But then the question of what value is and why, for example, why can the GDP of the world just keep going up? Why can there end up being more and more value in the world? And, you know, that humans are humans the way they've always been. Why is there more value in the world now than there was in the past? I mean, I have a theory about that now, but
well, that be a function of the, you know, material output of what's being manufactured, what's being done, goods and services.
Yeah, right.
I mean, the sum total of human activity.
Things were always being done.
That's the formula, yeah, that there's something, what's driving the formula to be true.
Right. I mean, you know, we've produced...
That's a story of motivation, I guess.
Well, we've produced more, what was it? We've, the artifacts we've produced are now, let's see, the artifacts far outweigh all of the life on Earth. The artifacts of humans far outweigh, in terms of mass, all the life on Earth. The concrete structures we've built weigh more than all of the ants and so on the Earth. So what? But, you know, my current theory, which might be wrong, is that value is associated with discovering computational reducibility in the world, and that the fundamental source of value is human mortality, is my current belief. That is, that the thing is, what can you do in time? That there are things which, if you could spend an arbitrary time, you know, speeding things up has value because humans are mortal, is one possible theory. I don't know if this is right. This is part of what I have to figure out. But you know, that's a yeah, that's sort of a meta point there. I think but I mean, to this point about, I mean, there are other fields like linguistics is another field. I'm curious about whether there are foundational things that can be said. Again, it's like, it would be nice to know kind of what is the fundamental problem of linguistics? You know, is the fundamental problem of linguistics kind of, I think the fundamental problem is, perhaps one of the fundamental problems is, you know, well, one of the problems is compositional language the only thing you can get? Are there other forms of communication? What can be communicated with compositional language? What is the space of meanings that can be communicated with compositional language? I don't know. These are things that, and you know, you can, yeah, anyway, and I mean, then there are questions like, is it inevitable that you have nouns and verbs and things like this? And is that some kind of sort of necessary feature of the general idea of language and so on? Anyway, lots of questions. All right, I better go because I have to do something else here, but it's nice to have a chance to chat with you guys, and hopefully we'll have another chance. I'm not sure if we have another scheduled interaction, but as I said in the preamble to this winter school, this is my way of getting to know lots of interesting people, and I like to continue these interactions. So, all right, I should run off. But nice to chat with you all, and
Thank you.
Thank you.
till the next
Thank
time.
you so much, Stephen.
Thank you.